Today we're going to learn about the simplex method. This will allow us to solve maximization problems that have problem constraints of the form less than or equal to. The graphical method works great when you only have two decision variables. That means we can graph in two dimensions using an x-axis and a y-axis, and if we only have a few constraints. However, if we have a very large, complicated problem with many constraints, or if we have even a simple problem with more than two decision variables, we need something else. We will use something called the simplex method, which was developed in 1947 by George Dantzig. The simplex problem is easily automated to allow computers to solve problems with thousands of variables and constraints. Let's start off with some vocabulary. We'll learn our vocabulary using this example. This, hang on. Alright, what is my problem? This is an example of a standard maximization problem. Has a linear objective function. This is our objective function. By linear, we mean that we have all of our variables to the first power only. You don't see any x squareds or y cubes in this problem. In each of our constraints, we have less than or equal to a positive constant. We also have non-negative constraints for the decision variables. This is a standard maximization problem, and it is now written in standard form, as described here. What we're going to do is to convert our constraint inequalities into equations. That way we can put them into a matrix. Remember, in a matrix, each row can represent a linear equation, and our coefficients in our linear equation will turn up as entries in the matrix. We're going to use something called slack variables to do this. So here are our constraints. We have 8x1 plus 2x2 less than or equal to 400, and we have 2x1 plus x2 less than or equal to 120. The first constraint we will write as an equation, 8x1 plus 2x2, and then we're going to add something called the slack variable. I'm calling mine S1. I'm going to leave a little bit of space here and put my other side. Our second inequality we will write as an equation, 2x1 plus x2. Now we're going to add a second slack variable, which I will call S2. So S1 and S2 are the slack variables. The reason we have to do this is that we cannot put an inequality into a matrix. A row of a matrix represents equations. In other words, we need equal signs, not inequality signs. So what we're going to do is we are going to let S1 represent the amount of slack between the total of 8x1 and 2x2. Those are going to give us some total, which has to be smaller than or equal to 400. S1 represents the slack, or the difference between the total of these two and the 400. S2 represents the slack, or the difference between 2x1 and x2 up to 120. Remember that our totals here of these first two variables multiplied by their coefficients cannot exceed the right-hand side. It could be equal or it can be smaller. It cannot be more. Therefore, our slack variables, S1 and S2, have to be non-negative. In order to satisfy our constraints. So these are not allowed to be negative. If they were negative, we would have the total of the first two terms. If we put a negative number, that means our total of these first two could be larger than 120. And we do not want to allow that. We need it to be smaller than or equal to 120. If our slack happens to be 0, for example here, if s2 were 0, that would mean that 2x1 plus x2 was exactly 120. So what this does is it lets us revise our system. This is what it now looks like. Here are rewritten constraints. And all of our variables, including the newly created slack variables, have to be non-negative. If they're negative, our constraints are violated. Now we're going to rewrite the objective function with all the variables on one side. Here's what it looked like before, in case you forgot. So now we're going to subtract 90x1 and 25x2 from both sides. So now I have negative 90x1, negative 25x2 plus p is equal to 0. We're going to put that together with the constraints that we've rewritten with the slack variables, and we're going to have something called the initial system. We're going to list the constraints first and the objective function last. Leave yourself some room so that we can have room, because some of the variables will not appear in all the equations, and if possible we would like the variables to all line up nicely. Here's my objective function, and I'm going to think of the p as being a separate variable, which means I'm going to leave a separate column for it when I eventually write the matrix. And there are my non-negative constraints. Now we use this to create an augmented matrix. Augmented matrix just means we're going to augment the right-hand side onto the coefficient matrix as we've done before when working for matrices. It will help if you'll write the variables above the columns. It will keep you from getting mixed up and make it easy to see what your solution is. Okay, so now we write the coefficients of x1, so that'll be 8, 2, negative 90. x2, I have 2, 1, negative 25. s1, 1, 0, 0. s2, 0, 1, 0. p, 0, 0, 1. And now my right-hand coefficients, 400, 120, and 0. It is certainly optional, but you are welcome to draw a vertical line to visually separate your right-hand side, and you can also draw a horizontal line to visually separate the bottom row from the others. Remember that last row comes from the objective function. We are going to think of these These are sometimes called indicators. What they will do is they will help us to proceed with the next step of our simplex method. This is our initial simplex tableau. Now we are going to learn about something called the pivot. To perform a pivot, the first thing we need to do is to choose the pivot column. First, I will rewrite my matrix. Okay, here's where we're going to use the indicators on the bottom row. We are going to choose the most negative in the bottom row. In our case, that'll be this negative 90. We're going to choose this not because it comes first, but because it is the most negative, the negative number that is largest in magnitude. So I'm going to circle this column. This is our pivot column. Now we come to the other side. For every non-negative entry in the pivot column, we divide the value in the rightmost column by the corresponding non-negative value. In other words, this 400 I will divide by 8, which will give me 50. I'm forming quotients by taking the number here, dividing by the number in the pivot column as long as it is not negative. So here I take 120, I divide by 2, this gives me 60. What you want to do now is choose the smallest quotient. This is the smallest. We do not do the bottom row. Notice, if I were to do the bottom row, I would need to be dividing by a negative. We never form quotients by dividing by a negative. That is going to mean that we do not ever form quotients using the bottom row. Okay, now we're going to choose this for my pivot row, whichever one gives you the smallest quotient. So the place where they intersect, right here, this will give me my pivot element. What we want to do next is we're going to do a pivot operation on that element. Here's what we mean by the pivot operation. Using row operations, we're going to put a 1 in the position of that pivot element, zeros everywhere else in the pivot column. And we're going to do this in a very standard way. Here's my matrix again. Okay, and here is my pivot element that we have previously chosen. I'm going to show you in this section how to do the pivot operation by hand. You should certainly be able to do that and understand it, but I encourage you, once you know how to do that, to take advantage of modern technology, including graphing calculators and computers, in order to do the arithmetic of the pivot operation for you. So the first thing that we want to do is we want to get a 1 in this position. And we want to get zeros here. Okay, just as in row operations, what we're going to do is the first step will be to multiply the first row by the reciprocal of that number. So this will be 1/8, row 1, and we'll put it into row 1. So that will give me 1, 1/4, 1/8, 0, 0, 50. Notice that 50 is the smallest quotient that we had found earlier. I'm going ahead and recopy the second and third rows for now. And then we need to get zeros in the places that we want. So we want zeros here. To do that, we're going to take -2, multiply by the row with the leading 1 that we just placed there. So that'll be row 1, add it to row 2, and put it back into row 2. We're also going to take the opposite of -90, which will be +90, times the row with the 1 in it, add it to row 3, and then back into row 3. When we do this, we should get 1, 0, 0. And then last we have 50, we have 20, and we have 4,500. Let's put the variables back on. x1, x2, s1, s2, p, and the right hand side. Notice in our pivot column we have now been changed to something that looks like a column in the identity matrix with a 1 and the zeros. We have accomplished one pivot. If we were thinking of what this equates to in the graphical method, what we have done is we have now moved to a different corner point. If you were to do this particular problem with the graphical method, you'll find that one of the corner points, when you evaluate the objective function, you end up with 4,500. Now we need to do another pivot. As long as there are negative numbers on the bottom row, which there are, this should say -5/2 in case you can't read it. As long as there are negative numbers on the bottom row, we are not finished yet. So we need to do another pivot. Okay, here is our previous matrix. Okay, here is our matrix. After the first pivot, what we're going to do is we're going to choose the most negative number on the bottom row, and in this case we only have one negative number, and so this will automatically be our pivot column. Then we come to the right hand side. We're going to form quotients using the right hand side and any positive numbers in the pivot column. So here we have 50 divided by 1/4, which is 50 times 4, which is 200. Next row we have 20 divided by 1/2, which is 20 times 2, which is 40. This is definitely the smallest. Whichever one is the smallest is the row that we are going to use for our pivot row. So now I circle this row where the row and the column intersect is our pivot entry. So that 1/2 is the element we're going to pivot around. Again, this time I will do them by hand. So I need to get a 1 in that position. In other words, we want a 1 here, and we want to get zeros in the other positions. Okay, so the first thing we will do is multiply that second row by the reciprocal of that pivot element. So that'll be 2 row 2 into row 2. First row stays the same. Last row stays the same for the moment. I'll do that separately. Okay, so we want to get our zeros here. So to do that, I need to do -1/4 times the row that has that leading 1, which is row 2, add it to the first row, back into the first row. And also I will do the opposite of the -5/2, so that's +5/2 times the row with the leading 1, which is row 2. Add it to that third row, and then back into row 3. This should give me this matrix. Make sure that you do the details for yourself so that you know you're okay with doing them correctly. Okay. Now, when we look at this, we look to see if there are any negatives in the bottom row, and there are not. That means we have no more pivots that we need to do. Let's go back. Okay, I'm going to rewrite my matrix, my final tableau right here. x1, x2, s1, s2, p, right hand side. Okay, and I'm going to go ahead and reinsert my horizontal line, separating out my objective function, and my vertical line separating my right-hand side. Now, here we have to learn about how to determine what solution is represented by this tableau. The variables that correspond to columns that look like columns of an identity matrix, those are going to be the columns in which we have a 1 with zeros everywhere else in the column. Those we call basic variables. The others we call non-basic variables. So in our case, these two are serving as basic variables. And also the p, which always will be basic. And then the non-basic variables are these, S1 and S2. Right now we are calling these non-basic variables. Every time you do a pivot, these change. The non-basic variables we will think of as being set equal to 0. So what we have is, if we translate each row of our matrix into an equation, we have, for the first row, we have x1 plus 1/4 s1 minus 1/2 s2 is equal to 40. And for the next row, we have 0x1 plus 1x2 minus 1/2 s1 plus 2 s2 is equal to 40. And then for the third row, we have 10 s1 plus 5 s2 plus 1p is equal to 4600. Okay, so now we think of setting s1 equal to 0 and s2 equal to 0. What will that do? Notice each of these, if I look at my first row, that means I'll have x1 plus 1/4 times 0 minus 1/2 times 0, which is 40, which will give me x1 equals 40. If I move to the second row, my x2 is still there. The others, the s1 is getting set to 0, s2 is getting set to 0. Therefore, I have x2 equals 40. If I look at the third equation, so this s1 is getting set equal to 0, s2 is equal to 0, so those first two terms are gone. So what does that give me? P equals 4600. So that is what we have. Basically, the columns that have, here's how I like to say it, the columns with the junk in them those variables are set to equal to 0. So what that means is you could just think of covering up those columns, and then you could read the solutions for The remaining variables, which are called basic variables, you could read the solutions for those right off the matrix. Here are a few notes about the simplex method. If there are no positive numbers in the pivot column, then we cannot perform a pivot, and we conclude there is no optimal solution. This can happen. If there is a tie for the most negative value in the bottom row, you can choose either column to be the pivot column. Unless the problem turns out to be one with no optimal solution, you will have multiple values of the variable that give the same maximum. In the graphical method, this corresponds to the situation in which the slope of the objective function matches the slope of one of the constraints, and therefore instead of being maximized at a corner, it's maximized on an edge. If there's a tie for the smallest quotient, you can choose either row. The pivot element is always positive and is never in the bottom row. We will never be pivoting around something in the bottom row.